There.
Okay.
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 Uh, so I'll be talking about three things, hopefully. So first, I'm going to define what is the inverse Ackermann function and the Ackermann function. And then I'll go into two problems. One is about arrangement inquiries, and then how the inverse Ackermann shows up there, and also about union find, which is maybe a little bit more famous. So the inverse Ackermann function, it kind of discusses like some of the orders of growth that computer scientists care about. So like we have linear, we have logarithmic, log star. And then, so here's the definition that Chargin gives, because Chargin is cool. He defines two base cases. If an Ackermann function is a function of two variables, you have I and j, and it's defined by this recurrence. I think it's probably best to go through like some examples of like what this recurrence means. So first, maybe a QC. So by definition, this is going to be 2n. And then we can discuss 1n. So by the definition, this was a 0 of a 1 and minus 1, which is, and so you get 2 a 1 and minus 1. So this is the recurrence for when a equals 1. Do you people know what the solution is by any chance? Yeah. For a 2n, we get a similar thing where we get 2 to the a 2n minus 1. Do people know the solution to this recurrence? Close.
It's 2, like 2 to the 3 of them.
So it's 2 to the 2 to the 2 over there's n times. I think it's called iterated exponential.
Oh, wait, that's the goals up first.
So Ackermann function grows really, really quickly. Yeah, really quickly. A3, I don't know what it's called. It goes up too quickly. So, and then you can define the inverse Ackermann as the smallest j such that aij is greater than or equal to x. So alpha 0n would be n over 2. Alpha 1n would be log n, because this is the inverse of 2 to n. Alpha 2n would be.
Wait, I have a question. So
Yeah.
it's not, is it only defined for integers, or how can you like?
It's defined for positive integers,
Okay.
not negative integers.
So like if it's, it would be like floor log n, or like.
Yes. There's some floors I don't care about. But yeah, technically you need floors and or ceilings.
Okay.
That definition's good at all. This one's a little bit more relevant to the like specific things I'm going to talk about. So in this definition, you define inverse Ackermann like as the inverse of the Ackermann function. You can also define it recursively using you can also define it recursively, and the definition gives the same things. So alpha 0 and I found it 1 equals n over 2. Why did I do it down? And you can define alpha 2n would be 1 plus alpha 2 n over 2. So you get a similar recurrence, which has a solution of log n. Yeah, but yeah, I think you're right in that you need the floors. Ceiling floors. So kind of the way to think about this sort of recurrence is that you have a recurrence tree, you start at n, and then you go to n over 2, you go to n over 4, and then until you get to 1, and that's where you have your zero cost. For every one of these nodes, you have a value of 1. And then basically for this recurrence tree, you want to just find the height of this recurrence tree, and that's going to be like the total number of work that you did. Okay. So this recurrence tree, way of solving recurrences is going to be very prevalent throughout this talk. So also we can define a similar function with just basically the same thing with a similar base with a different base case, where you have the root j instead of the j/2. Sure, I'll solve it. I'll solve the one n. This is root n. Beta 2n is beta of 2 root 1 plus, yeah. Does anyone want to try to figure out what the solution to this recurrence is? So you have n, and you go to root n, root n, or n to the 1/4. 1. Half the log? Almost. It's log n. Yeah. And kind of the way you can try to prove this is you can prove it inductively. So log of, so we can verify that it satisfies this recurrence. So if we want to do log n is equal to 1 plus, we want to verify this equality 1 plus log root n. We can do that by, so log rules, this 1/2 comes out, log 1/2 log n. Now you have a product of two things in a log equals 1 plus log 1/2 plus log n. And this is 0. Yes. Another way, so you can verify recurrences by plugging them in. That's what I just said. Everybody clear about the function? Yes.
So the first function is the Ackermann function. Beta is something else.
Alpha is the inverse Ackermann. Beta is a different function that's has the same order of growth with a different base case. I don't think that's named. Okay. So now for the first column that you guys might have heard about, it's called the range mimicries. Here is the statement. So what this the statement is that we're given an array of numbers from 1 through n, and then our user could give us like a range to query from. Maybe it'll take from this range or from this range. And then we want to give the user what the minimum of the numbers is integers. We want to tell the user what the minimum number in the specified range is. And in particular, we're going to parameterize it by a value k, which is kind of how many steps we're allowed to do this query in. And I'll define steps. I'll give examples of what the steps mean. The steps are basically how many calls you can like query the array. And then the theorem is how you can do this very quickly. That has a type. There should be an end. That's a type. Oh, and this is so when you have one step, basically when you're only allowed to like look at the array once, the only thing, and I should ask you, so this is the algorithm to pre-process. You're given a lot to pre-process. We want to find the minimum time and space to pre-process the array such that whenever the user wants to query it in the future, then we can return the answer very quickly. So in particular, if you want to have one step, then for there's n squared different like intervals that the user could query from. So if we want our algorithm to work in one iteration or one time, then we will actually have to compute every single possible substring. So this is like the trivial case where k equals 1, and we have an O of n squared total time to pre-process everything. And then when we have more steps, we're going to do divide and conquer algorithm.
I'm confused exactly what is the step? Can you explain it? Like,
Right. So what's the right way to define the step? It's like kind of, so we're going to have like some sort of pre-processing data structure, like some sort of pre-processing like data structure like that holds a lot of queries, and we want to like figure out how many times we need query from that data structure in order to get our desired answer.
okay. So each query that we from the data structure is a step. Or like,
Yeah. So if we have k equals 1, then basically our data structure has to store every single possible substring.
Okay.
So that's why for k equals 1, we have an n squared, like total time and space to pre-process the array.
Yes.
And in part, so we will go through like every index and then find every substring and then find like the minimum of that.
Okay.
For k equals 2, we are going to do this kind of with a divide and conquer algorithm. So we're given this array. We're going to differentiate between two types of queries. I'm going to divide this array in half. We have queries that are only on one side of the array, or we have queries that kind of span this middle line. So if we have queries that span the middle line, what we can do is we can take the minimum of this value of this range, the minimum of this range, and take the minimum of them. So that's then this will be a k equals 2 step algorithm. So then like we're doing two queries into the data structure and then knitting them together. And for these ones, we will recurse down our pre-processing algorithm on the n/2 size array. And we want to figure out how fast or how much space we need to pre-process this entire array in this manner. So in particular for these intervals that span it, we're going to pre-process every interval that on the left side that ends at this block. So basically every suffix and every prefix of this. So every suffix, so maybe like this is n/2. We create this range, this range, this range, this range, as well as these ranges on the other side. So the suffixes and the prefixes, and recurse on this. So for these, we have a total of n intervals that we need to compute. And then we recurse down to a recursive calls on each half, which leads us to like so then we can write a recurrence for the total number of space that we need to pre-process this array as 2t of n/2 plus O of n. These are going into the left and right halves. This is to figure out this like divide down the middle, like the suffix prefix combination. And I'm sure people know the solution to this recurrence. What is it? Yes. And again, the way to do this, the easiest way to do this is by using a recursion tree. You start with like your tree for n, and then in the first level recurrence, we divide into two columns of n/2. And at this level, at each level, we see that we're going to always have n work total. Sorry. So we have n work for every level in the recursion tree. This will be 4 problems of n/4 size. And then in total, this recursion tree will go on to log n levels. Yeah. Yeah. So we use our algorithm to figure out what is the minimum amount of space to pre-process this n/2 size using 2 queries. And then if the user gives the range that's only in this tab, then we basically recurse down the left tab.
So would it be 2 steps or like log n steps?
So we're going to build a data structure that like has every range. It'll still be 2 steps because our algorithm for this only returns in 2 steps. Did that make sense?
You know, I guess I'm confused about if your query is entirely in one tab, right? And it's not just like a prefix or suffix or something. Then how are we going to compute that? We have to do more splitting, more steps, right?
Right. So there's going to be one point in our array, like what maybe what we might subdivide is further into here. We're going to recurse down these like quarters. So when we do one more recursive step, then this is going to be a prefix and a suffix of something else in a recursive call.
Is that good stuff basically like we're gonna use 2 substrings of the array basically. Like that's like k steps is bounded by like the use of most k preprocessed substrings of the array. So it's not about how many recursive calls down.
Yeah. Sure. This is not good enough.
What is 3 days?
Thank you. The recurrence? Do you have a question?
Well, are you gonna do that in 3 case or just like?
I can't do the 3 case. Should I do the 3 case? It's almost the same algorithm. Yeah, I'll do the 3 case. Actually, I'll do the 4 case if that's okay. Or I'll do the 4 case because that extends a little bit.
Okay.
For the 4 case, we're going to do the similar things where we divide our array. But in this case, we're going to divide into log and size blocks. And then we're going to have how many blocks? We're going to have n over log n total blocks. When we make the query, we're going to have like 2 types of queries. We have like short queries, which are contained entirely within a block. To do these queries, we're going to have to recurse down. We're going to pre-process by recursion. Otherwise, we have some sort of long queries that span multiple different blocks. And we can break this down. Yeah, so case steps. We're going to break these down into, we're going to find the prefix and suffix of this. And then use our algorithm to recurse on k minus 2 steps. This is recursing with k steps. This is like description of the arrangement query makes sense. So we do the same thing where we divide our array into blocks. In this case, for k equals 4, we're going to divide into log n. And then we want to use our algorithm for k equals 2 steps on like these blocks. Sorry. We have an array of blocks of n over log 2 blocks. We want to use our when we have a long query, we have this prefix and suffix pattern, but we also have like some range of that spans the entirety of our blocks. So the idea is we make like a subarray or an array A prime that is of size n over log base log n. And then each element in this A prime is going to be the minimum of a block. So this is going to min of like A0 through A log n. And this goes into this block. So that when we do this, we can query into this data structure using 2 steps. Is that figure out? So if we want to analyze like how much this takes in total, we're gonna have to consider most like the recurrence. So we first have to have this prefix suffix pattern. on every single like block subdivision. And we're gonna have about 2n or O of 2n. O of n, different like prefixing suffixes, like starting at each block and starting at each block division. We also need to recurse on each of these blocks to figure out how to answer the query using 4 steps. We're gonna have exactly n over log n of these blocks. And we're recursing with 4 steps on a problem of size log n, because that's the size of each block. And finally, we're gonna have to create a subarray A prime, where we take the middle of each block so that we can query it in the future. This size A prime is of size T2 of n over log n. So this is like the total recurrence for this entire, I'll call this Ti. And then if you want to solve this recurrence, we first remember that T2 was T2 of n was equal to n log n, which we saw just earlier. So then when we have T2 of n over log n, this is bounded above by n. So we get 3n plus n over log E4 log n. Yeah. And this recurrence, we can solve it by a similar means to previously with the recurrence tree. Maybe we start with a recursive problem of size n, and this does 3n work. We will split into n over log n, n over log n, different recursive calls, each of size log n. So the total number of work for this layer would also be 3n, because yeah, the total number of work for this layer is also 3n. Every layer will have a total work of 3n, and this height has a height of log star. Yes.
Log star
So log star is how many times we need to iterate the logarithm operator until we get to 1.
okay.
Yes.
Would you get E2 of
P2 n over log n. Okay. So and to answer, I distinguish between short queries and long queries. Short queries are when they start and end at a division. And then long queries are when they span multiple blocks. To answer this type of query, we're going to first take the minimum of these elements. We're going to take the minimum of these elements. And then we're going to we need to figure out some way to get the minimum of all these elements.
Oh, I know.
Yeah. So we make an array of the blocks. And then we're allowed to use 2 recursive calls on this like smaller array. So then the solution was T4 and is equal to 3n plus 3n log star n. And for arbitrary k, we basically do similar steps where we divide into blocks of certain sizes. We will recurse down, we find the prefix array, we find like the prefixes and suffixes. We recurse down each block. And then we also have to recurse to figure out to preprocess the smaller array of each block, of the minimum of each block. In particular, the size for an arbitrary k, the size of each block would be defined by this lambda function, which is alternating between the alpha function and the beta function that I defined earlier. So For even k, I will use the output. For odd k, I use the beta. That's the recurrence here, and the solution is nk lambda k. Yeah. Any questions about great family queries? Yeah.
All the versions we do that.
Yes.
And then the data structure, so it's in the input blocks and well.
So we need to store the minimum of each like prefix, suffix that ends at a block division. We need to store the minimum of like each block. Like the minimum of each block. And we also need to find the minimums of like each smaller block. Or like enter within block queries.
Is this like a lower bound to like?
It's tight somehow, with an asterisk. So this is tight if the only thing you're allowed to do is take the minimum of like a range. There, some, or the way that the paper uses it is if you have any, if you're only allowed to use an associated, associated binary operation, which is minimum associated binary operation.
But it doesn't assume that like, f of a equals a, right?
It does not. This algorithm works for like a sum, for example.
So it's type even if you assume that f of a equals a. Like if you allow overlapping,
Yeah.
that doesn't change the math.
Yeah, so this analysis is type even with like max and mins. But because these are integers, like there's a different algorithm that uses the 4 Russian techniques that has a better bound, but that uses things that aren't just max and min, like it does addition subtraction. Yeah. So this is a linear query. You have a very similar result if you want to query into like a binary tree. If you want to find like the ranges of binary tree. That's something to think about. Okay. So that was the first result that I wanted to share, which was about recursive queries. We can do this using, I think, a pretty simple recursive algorithm. Is it simple? Relatively simple recursive algorithm. And then the next problem I wanted to like kind of discuss was about disjoint sets. And do people know what a disjoint set is? Yeah. But anyways, yeah. So disjoint set, shall I still give a review of them? Or is everyone okay?
I think it's good to talk about.
Sure. So disjoint sets, they support 2 operations. They support an operation called union, not an operation called find. Given a set of elements. Sure, given a set of elements, we can group them into like disjoint partitions. They don't really have to be contiguous in an array. Yeah, we're given a set of elements. We can like divide them into disjoint sets. Maybe like one set is this, another set, another set. And then we have 2 operations, which is to check if 2 elements are in the same set. Maybe, and for example, these 2 are different sets. Or we can modify our disjoint sets to make these into the same disjoint set. And the claim is that this operation can be done very, very quickly. How quickly? I should say somewhere. I don't see it. This algorithm takes the inverse Ackermann function time in the amortized sets. So which is really, and we saw how fast, how slow the inverse Ackermann grows. So just some implementation details. Yeah, find. We normally represent disjoints as some sort of uptree in an array. So if all our elements are going to be integers between 1 and n, let's say our set
is the integers 1 through n, then we can represent this as an array where the first element is going to be element 1. And then 2. And then every disjoint set, we're going to designate a set leader. Maybe arbitrarily we could define this as the set leader. I can't spell. And this is going to be like the canonical element of our set. So to check if two elements are in the set, two elements are the same disjoint set, we're going to check if they have the same set leader. And so find is going to return the set leader. Every element in this array is going to point to its parent. Or if it's a set leader, then it'll have -1. Pointing, I mean, this will have the index of its parent.
So implementation,
We're going to be discussing the implementation that uses two optimizations.
mainly we're gonna do union by rank. And also union, and also path compression. So what do I mean by these two optimizations? So we have this sort of like disjoint set structure, where every element in this array will point to its parent. So the amount of time that it takes to find a canonical element is going to be proportional to how high, how deep this, or what is the height of the maximum tree. We're going to denote that the rank. And then whenever we want to union two disjoint sets together, we're going to union by the one that has, we're going to make the one that has less rank. We're going to merge this one into this one. So we're going to change the set leader. If we want to union two disjoint sets together, all we have to do is we have to move the pointer of the set leader to the set leader of next of the disjoint set that has larger elements.
So if you union two set leaders, how does it work? Because both of them will have rank.
So this, when we union them, this is no longer a set leader, it will just point to this set leader.
Like, what if you union? What is the rank, like how long it takes to get to the set leader when you find the root, or is it like the size of the set?
The rank is going to be the height, the maximum height. Maximum depth. Maximum height.
Oh, I see. And then you just keep track of that, but after the year back.
Yeah,
So
so
height changes.
with path compression, when after I unit these two nodes together, let's say I want to find the set leader of this element. Then the set leader of this element is the same as the set leader of this element because this is pointing to this. And this points to this, so that I can set this for my next query. I can just directly say the set leader of this element is this element. Because we don't have any like splicing operations, the set leader will always go up. So path compression is every time we do a search, we're going to set the parent to the parent of this parent. We set the parent to the parent of its parent, where y is the parent of x. For find, we just return the parent until we the set leaders point to themselves. So while y is not a set leader, we go up tree, and then we compress it afterwards. For union, I said that we union by rank. So we set the leader of the one that has the smaller rank, or we set as the leader of the one with the larger rank. For union, we want to union the two set leaders together. Any questions?
Okay, so the joint sets. So in order to analyze the joint sets, I'm gonna be giving the analysis that Erickson gave in his textbook. So this analysis relies on a few properties. So the first property is that leader ranks only increase. As Ethan said, the rank of a set can never go down because only time, the only time they change is when we're unioning two sets together, and that's when we increment them. Yeah. The size of a set is going to be at least double, at least two to the rank. And that is, the bar means it's a set leader. And that is going to be because, whenever we have two sets, the rank only increases if they're both have the same rank. Because if one has smaller rank, then we could just merge it directly into the other one without increasing the rank. So, this has rank 2. We can point this one to this one, and because they have different ranks, then the rank of the entire bigger set doesn't change. Which is why we get doubling every time we increase the rank. And also, we also have a cap of how many elements of rank of a given rank there are. And that is for the same reason as this. And this analysis is what's called an amortized analysis. What that means is that instead of considering each individual union operation, we're going to consider M unions. And we're going to consider M unions. And then we're going to, if this takes like some function f of m time. So on so in the amortized sense, union takes f of m over m on average. In the amortized sense. This is going to be the total time it takes to do m different operations. So that in the amortized sense, each operation takes f of m over m. To make this analysis like a little bit more straightforward, we're going to be looking at number of pointer operations. So that means like every time we change one pointer to a different one, we add one to the number of pointer operations. And now for the details, find we want to analyze the running time of union find, which is two subroutines. Instead, we saw that union is simply two calls to find, and a union leader has a recursion. It's a constant time operation. So the only thing we need to do is to analyze find, and then that'll also give us the running time of union, basically for free. Also for find, we see that is also just a call to compress, where compress is doing the path compression. So all we need to do is analyze compress, and then if compress is some time complexity, then find and union are given the same time complexity. Another thing is that we can make all calls to union before we do compress. So as I said, we're counting the number of pointer operations. It doesn't matter in our analysis, it doesn't matter if we change the order of the pointer operations if the total number is the same. And I'll give a diagram for why we can union before compressing. And we're going to introduce a second operation to make the analysis recursive. So I claim that we can always do every union before a compress, where the total number of pointer operations does not change. What does that mean? So on the top we have a compress followed by union. On the bottom we do the opposite order, and then if you count the pointer operations, you get the same amount. So this is compressing everything in pink, whereas this is still compressing everything in pink because even though we do a different order. And then after shatter, our destroyed set is basically a force. What I'm going to do is I'm going to say we have two partitions of our forest. One
one of small rank and one of large rank. And this rank is going to be a threshold X that we're going to set later. So two subforts. And what, so if we have a up tree where everything points up. If I want to compress this, I don't want to move this one to this one. Instead, I will set the pointer of this to itself because this is below some threshold S. So this gives us like a recursive way to analyze the data structure. And it's called, the operation is called shatter. Yeah. So as I said, this is the amortized analysis. So we're going to count the number of quarter operations of M compressed calls. Of M compressed calls. And just parameterizing everything, get N nodes. And rank R of the maximum set. The rank of the maximum rank of the set, of any set. It's always good to have base cases when we do analysis. T M and R is going to be less than NR. What does that mean? It means that the total number of Porter operations of a disjoint set of n elements is bounded by NR. And that is because every single element can only change rank R times because it's always increasing. And since the maximum rank is R, we're bounded by NR total, which is a very generous amount, but it's useful. So we have a forest. We have a forest of F what's the minus? F minus and F plus. That's false. F plus and F minus. When we do compress, we have nodes like we have n plus elements in the top forest and n minus elements in the bottom forest. We distinguish two cases where we want to compress nodes that span it. We want to compress this is a leader of this is like X and this is X bar. We want to compress from here to here. We want to compress from here to here, or we want to compress from like within a forest, within forest plus, within forest minus, or between the forest. And then I say that I'm just going to give names. We have M compresses. And then we have M plus like compresses on F plus. And we have M minus compresses on F minus. And then M plus. So I'm just going to split the sequence of compresses into ones that are on the top tree and the bottom tree. And then we have this recurrence. And what does this recurrence mean? It means that I see this. So the total number of time to do the recurrence to do this all M compresses is going to be the sum of the ones on the bottom and the top. Because like we're just splitting the compressors into two segments. But also because we introduced a new operation called shatter, we have additional factors. So when we have something that when we want to compress two elements that span different trees, then what we're going to do is we're going to we want to compress every element from here going to this. What we need to do is we need to compress up to here, and then we need some factor of the number of elements like above it. So then that's where these two factors come in from. The M plus is every operation on the minus to the top, and an extra N because that's like shatter can only touch every element once.
because you can like shadow multiple, we don't ever shadow multiple elements for the same. And as I said, we have some distinction S. We have some threshold S that distinguishes whether whether like we're in we're the plus tree or the bottom tree. So then we had that bound of NR for the number of time. Since so then we know that n plus is going to be less than n over 2 to the s. That's because the maximum rank of this is going to be s. So then by our earlier lemma, number of elements is going to be less than like 2 over the maximum rank. We have we have the number of time, we have the time on the top tree is less than Rn plus. And then for the numbers we have n, which makes sense. And then we by using the recurrence here. By using the recurrence, we can plug in the numbers. And remembering that plus is equal plus minus equals n. We can subtract n to both sides to analyze the time complexity of T prime, which is something that we to get this recurrence. And then we need to solve this recurrence. The easiest way to do this, we've already seen this recurrence before. Yeah, we've already seen this recurrence before. Which is I haven't written it down, which is 2n log star r. And that's because we have log r. Every time we go down this recurrence, we decrease the r by log into log r. So then because the base case is when r equals 0, that's when n is equal to, that's what work is constant. This recursion tree has a height of log star r. Each recurrence tree we have 2n work. So we get this bound of log star r for the total number of time it takes to do uncompressed operations. To improve this analysis, we realize that we start by having this bound, which is a very generous bound because we just figure out something better. So then we can plug in 2n log star r in front of our recurrence. And then choosing a better factor of s, now that we have more knowledge, we get plus 2n. Solving this recurrence has a solution of log star r, which means that it's how many times log star is how many times we need to iterate log until we get to 1. Log star is how many times we need to iterate log star in order to get to 1, which is smaller. We can repeat this analysis as many times as we want. Cm plus c plus 1n log star c, where c is how many times we want to recurse down a tree. Log star c is another word I use for alpha cr from the beginning of this talk. And then choosing the right factor of c, we can choose c is equal to alpha of n, where alpha is the Ackermann function, to get our final bound at the total number of point operations. In case we do compressed operations is alpha n, which means in the amortized sense, t and n is alpha n, or compressed takes alpha of n total point operations in the amortized sense, which is what we wanted to show. Are there any questions? Sorry, I sped through the rest because we're out of time. Yeah.
So can you explain again what you see?
Huh?
Can you explain again what you chose for C?
C equals alpha of n. C equals alpha of r. Actually, I skipped the few steps here. So T and R equals C plus 1 and alpha CR. Setting C equals alpha of R, we get C alpha of R plus M alpha R plus alpha R and alpha of C alpha R is a constant. And we also know that M is greater than equal to N. So then we have a final bound of N alpha of R.
What is the single argument of the function?
The single. Find that. The single alpha function is min. It's the smallest. It's the smallest n such that the two argument on 2 is greater. Is greater than equal to. Min I such that is greater than equal to n. It's the smallest number that grows past n when applied to 2. I think. Yeah. Any other questions? Yeah. Why is it an R? Because we chose alpha R to make this become a constant. We get an alpha R. I think this is like this is a constant factor of an alpha n because R is less equal to. That was because every time we go down the recursion tree, we like have this bound on R. Like a recurrence, every time it takes R, and we get a log factor. Or a log, like this has a log factor, because that's us like going up into F plus. Yeah, so
It's just for the purpose of.
just for the purpose of analysis, we're gonna split into 2 trees so that we get this recursion that we can like solve.
And the purpose of it's just to reduce the range of what the down payment.
Yeah, exactly. So plus and minus. Yeah. That all? It's a very long thing that I stole from Emerson's textbook.